This talk is basically the antidote to most attempts to teach people how to do BLE, Bluetooth Low Energy, that is. Because most people, when they teach Bluetooth Low Energy, start with an OSI network diagram, and it goes downhill from there. I've attempted to avoid all box diagrams. I think there's a couple of tables in certain places, but that's as bad as it gets. And about halfway through the talk, I'm going to stop talking about how BLE works and actually go and build something that uses BLE, which, quite frankly, is the only way you learn anything, right? Anyway, the Bluetooth 4 standard actually includes 3 separate protocols. It includes what most people remember as Bluetooth, the stuff that used to go in those little ear things that did audio. That's Bluetooth Classic. But there's also Bluetooth High Speed and then Bluetooth Low Energy, also known as Bluetooth Smart protocols. Now, Bluetooth High Speed is based on Wi-Fi and has absolutely nothing to do with Bluetooth whatsoever. Classic Bluetooth consists of all those legacy Bluetooth protocols we're all used to and nobody wanted to touch because they're awful. Neither Bluetooth High Speed nor Bluetooth Low Energy, which we're going to talk about here, really share anything to do with classic Bluetooth whatsoever except the name. This was supposed to not be confusing. So let's get the confusing terminology out of the way right at the start. Bluetooth Low Energy, BLE, is marketed as Bluetooth Smart, branded that is. If a device has Bluetooth Smart Ready brand on it, that means it's a dual mode device. It talks Bluetooth Classic and Bluetooth LE. If it's branded Bluetooth Smart, not Bluetooth Smart Ready, it indicates that it's an LE only device, typically a battery operated sensor or something like that. And it needs a Bluetooth Ready device to talk to it. There is a small problem. Some Bluetooth Ready devices need software updates to allow them to talk to BLE devices. So despite the fact it says Bluetooth Ready on it, you might need to roll out a firmware update onto the device to actually make it talk to Bluetooth Low Energy at all. I'm not looking at you, smart Samsung, whatsoever. The hardware is willing, but the software is weak. So love them or loathe them, Bluetooth Low Energy has been supported by iOS since the release of iOS 5. And all the Apple iPhones since, I think, and iPad devices since, I think, the iPhone 4S have supported BLE, as well as all modern Macs, laptops, and desktops. They all support it. Things are a little different over the other side of the fence. Google was concentrating on NFC. It was betting its game on NFC for quite a while. So despite shipping hardware, most Android phones had hardware that supported BLE. There wasn't actually any software support in Android for quite a while. As a result, many manufacturers introduced their own libraries for dealing with Bluetooth Low Energy, and they were all incompatible. API level, it was not a great situation. It was a total mess, in fact. It wasn't until Google I/O back in 2013, I think, so 2 years ago now, Google announced that they were introducing support for LE in the core Android operating system. Unfortunately, the Android versioning problem, the fact that, unlike iOS, people that either don't or don't get the opportunity to update their Android operating system on their phone, means that even today, 2 years later, there's a whole bunch of phones out there that theoretically could do Bluetooth Low Energy, but right as of this moment don't. It probably doesn't affect anyone in this room because all of us actually know how to upgrade our own firmware, but for the bulk of the population, this is still a problem. So, compared to traditional classic Bluetooth, BLE is intended to provide considerably reduced power consumption. That's the whole point, low energy, right? And at a much lower cost as well, whilst maintaining similar sort of communication ranges. So manufacturers are claiming something like a 50-meter range for BLE devices. And more typically, I'm seeing something like 15 meters or even 10 meters reliably as a maximum range indoors. And possibly less than this, depending on the manufacturer, depending exactly on how the aerial is in the device, or whether you're in a stone building or in a building with concrete and rebar. Now, obviously, something is going to get sacrificed to achieve the low energy part of this. And that's the amount of data the link carries. So if you're confused about data rate and throughput, data rate is the raw bit rate, the theoretical maximum bit rate that can happen. And throughput is the measure of the delivered payload, stripping away framing and management packets and correction packets and that sort of thing. Now, in case you're wondering, there is much lower throughput here. You see that the theoretical data rate is actually pretty similar between Bluetooth Classic and Bluetooth Low Energy, but the achieved throughput for Bluetooth NG is much, much lower. And this is mostly, although not all, down to the smaller packet size and the smaller number of packets per connection event in the Bluetooth Low Energy protocol. But it's not all down to do that. There's a bunch of reasons, but that's the main one. So this is actually saying, what, a 270 kbps or something like that. I've actually seen and measured sustained real-world rates, throughput rates, ranging from 270 kbps all the way down to 35 kbps. If you're actually building applications around Bluetooth Low Energy, I wouldn't rely on anything more than about 85 kbps. There's a reason you can't do audio over this protocol. There also seems to be some manufacturer dependency between the different chipsets about the sort of throughput you can manage. And so it does hint that there's some sort of software dependency, some sort of stack dependency, BLE stack dependency on this figure. But a lot of it does seem to be down to conditions. But effectively, this is the trade-off you are making, power efficiency for throughput. A BLE peripheral device can survive on its own for months, years even, on a small coin cell battery. There's no way a Bluetooth Classic device or a Wi-Fi device can do anything approaching that. You're getting power consumptions of up to 100 times less for a BLE device than you were with Bluetooth Classic. But BLE is actually very different from Classic. Very different indeed. So you're probably used to thinking about radios as effectively a serial connection, like a telephone call between two phones. Once you establish a connection, each person talks and the other one listens. So you pick up the phone, you say something, the other person listens and then says something. It's a serial connection back and forth. And that most part, that's how all of us have used radios, whether they're Wi-Fi, whether they're Bluetooth, whether they're Zigbee or anything like that in the past. And the radios stay connected, even if neither person is saying anything, until they hang up and the call is ended. In systems like these, data is transferred using a queue, and when the data is read at the receiver, it's erased from the queue. And just as once my words reach your ear over the phone, they're out of the communication channel. Now, that's effectively how classic Bluetooth works. Bluetooth LE, as I said, is different. Instead of communicating one-on-one like a phone, Bluetooth LE actually acts like a community bulletin board. Each radio either acts as a bulletin board or a reader of the board. If your radio is a bulletin board called a peripheral in BLE parlance, it posts data onto the board for everyone in the community to read. If your radio is a reader, called a central device in BLE parlance, it can read from any of the bulletin board's peripheral devices that have information for which it cares about. If you don't like this analogy, and I admit it's a little strained, you can also think of peripheral devices as the servers in a client-server transaction, because they contain information that the reader is asking for. Similarly, central devices are the clients of the Bluetooth LE world, because they read information from the peripherals. Yes, oddly, in this analogy, the little distributed peripheral devices like sensors are the things that we're thinking about as servers. Odd, huh? There are two key differences between BLE's model and serial communication model. First of all, in Bluetooth Low Energy, data is exchanged asynchronously. You don't wait for it to come down to you. When you want it, you read it. If you're sending data, you don't bother to pair, you just publish it and let receivers get it when they want it. This makes Bluetooth Low Energy devices low energy because their radios are only on when a peripheral is advertising its services and when a central device is reading from the peripheral. In contrast to this, a dedicated serial radio is on all the time whether data is being transmitted or not. Secondly, data is not deleted when it's read, only when it's updated. That means that multiple central devices can read the same data from the same sensor, one after another. And this is what makes things like iBeacon possible, for instance. Now, perhaps most, if not all, BLE breakout boards, the things that are sold to makers so they can build their own Bluetooth Low Energy devices, pretend to look like serial devices. Now, this makes things much simpler from an Arduino end, from a programming end, but effectively it means they're faking old-style serial over this bulletin board paradigm, and it's not a good hack. It totally gets rid of the whole low energy part of Bluetooth Low Energy, which is a bit silly. Imagine, for example, if you want to control an LED connected to an Arduino from your phone via BLE. If we use a serial connection, we have to open the connection to the board, and then it sits there open, draining the peripheral's battery until a 1 or a 0 goes down that line, and then you close it again. Alternatively, you can heavily reduce the power consumption by using Bluetooth Low Energy as it was actually intended. OK, so let's summarize. We have peripheral devices that advertise services. These are normally things like sensors. Then we have central devices that discover those advertised peripherals, can connect to them, and explore the services they're offering. The services advertised by peripherals consist of characteristics with descriptors. So you have a service with a number of characteristics that have a human-readable descriptor attached to each one. Characteristics can be read or written, but can also be flagged for notification or indication. The difference between notification and indication is that indication comes with a confirmation message that you've actually seen the update. Funnily enough, due to the use cases, most BLE devices, indication is actually rarely used. Bluetooth uses universal unique identifiers, UUIDs, for many things, including services and characteristics and descriptors, and basically telling people that exactly what each of these things is. Services and characteristics must be 128-bit UUIDs, and you can generate these things from the command line with UUID gen, for instance. Bluetooth services that have been approved by the Bluetooth Special Interest Group are assigned 16-bit UUIDs. Now, there are a bunch of people that cheat and use 16-bit UUIDs for actual products that haven't been approved by Bluetooth Special Interest Group. This is fine for playing around, but if you're actually building something, please don't do this. And yes, I've actually seen shipping products by large manufacturers that have actually done this. That said, it's fine to reuse UUIDs if there are services and characteristics that meet your needs. None of these things are defined as Samsung's light bulb. They're defined as a light bulb. So if you're building another Bluetooth light bulb, you can just reuse the UUID that some other bigger company has gone in through the torturous process of getting a 16-bit UUID approved. But if you're making your own services and there isn't an existing 16-bit UUID, please use a 128-bit UUID. If you want to get started playing with Bluetooth Low Energy, I'd recommend taking a good look at the TI sensor tag. You can actually learn a lot about how BLE services are deployed, how they look on the wire, quite a bit from this little device. It's actually marketed directly to smartphone app developers rather than hardware developers, either for them to develop an app directly to support the sensor tag or as a hardware reference for more sophisticated BLE accessories. They've actually just come out with a second version of the tag. This is it. It's not quite as silly a shape as the first tag, which was a very silly shape indeed. And it's based around the Texas Instruments' new CC2650 chipset. It's a really good testbed platform and an interesting product, despite being blatantly something that's put out to market their chipset. The CC2650 is a wireless MCU that targets Bluetooth Smart, so BLE, that is, Zigbee, 6LoWPAN, and Zigbee RF4CE remote control applications. It's a fairly versatile little chip. The TI sensor tag comes with a whole bunch of sensors. This is the front of the board. It exposes 5 of the 6 onboard sensors. There's an IR thermopile temperature sensor. So basically, you can point this thing at something, and it'll tell you the temperature of the thing you're pointing it at. There's a barometric pressure sensor and a 9-axis motion sensor. So that's an accelerometer and gyroscope and magnetometer all rolled into one. There's also a light sensor on this side. And oh yeah, the CC2650 also gains us a couple of extra sensors on board. It's got its own temperature sensor, and it's got a battery sensor as well, so it can tell you how depleted the battery is. On the back of the board, there are 2 small contact switches just to the left and the right there. the status is advertised and via notifications. So you can actually pick up and use this to control smartphone apps, for instance. You can use this as a game controller. Alongside that, there's a buzzer and a microphone and a read sensor as well. The read sensor can be used either as a magnet detector, so you can detect large magnetic fields, or you could actually use it as a tilt switch. To minimize current, and I've seen this done in a lot of the well-designed BLE devices, all of these can be switched on and off independently. So you can actually spin down all of the sensors and really minimize the current draw from the MCU. And which is why the entire board runs off a CR2032 cell coin cell. The other nice thing about the sensor tag is that TI is selling it more or less at cost, or possibly even below cost. I think you can pick one up for about 25 bucks, and there's often deals where they'll just give you them for free. So if you want to if you're on the smartphone side and the Android side or the iOS side, and you're looking to develop against Bluetooth Low Energy, this is actually a really good test device to pick up just to get your hands wet with the protocol. It's got a range of different profiles, a range of different services that you can look at. There's also a bunch of BLE hardware around, cheap hardware, that makes building, or at least prototyping Bluetooth things pretty trivial. This is the Adafruit Bluefruit LE. It's a breakout board for the Nordic Semiconductor NRF 8001. That's it in the middle there. Out of the box, this board comes with a UART service, so it's faking this serial protocol on top of the bulletin board paradigm, which is exactly what I'm telling you you shouldn't do, but we'll get to that. While a relatively cheap way of getting yourself a BLE connection, there are a bunch of wires involved. So you might want to use something like this. This is a Red Bear Lab blend board. It's also based around the NRF 8001. But as you can see, it's directly integrated into the board. This is an Arduino compatible board. By default, it also ships with a UART service, which means we need to fix that in software. So this is Arduino BLE Peripheral. This is mostly Sandeep Mistry's work. It's an Arduino library for creating custom BLE peripherals with Nordic Semiconductor NRF 8001, but also their NRF 51822 chipsets. It enables you to create customized BLE peripherals compared to the basic UART service that most of these Arduino BLE libraries provide. Rather crucially, it takes out the step where you have to use Nordic's proprietary software. Up until very recently as the beginning of this year, you had to use proprietary software to configure the Nordic chips so that they would actually offer proper BLE services, so you could give custom services. This was their NRF Go Studio, and it was Windows only, and it was proprietary, and it was actually pretty hard to use. So rather crucially, this library means you can skip all that now, and the waste is that you have slightly more space used inside your Arduino. You can actually pull another version of this library that does require NRF Go Studio. You create a include file as the binary definition of the services you're deploying in it, and then you can just attach it to your Arduino sketch. Anyway, thankfully, we don't actually have to go there anymore. But this library only works right now for Nordic chipsets. The interface is generalized. And looking at the TI tool chain, it's possible that something similar could be built for that. But as far as I know, and I'm open to correction here, no one has done it yet. Building custom services for TI chipsets still requires their proprietary tool chain. And there's definitely nothing to integrate it into the Arduino environment as cleanly as this. So for now, if you want to build your own BLE thing and you actually want to use proper BLE services, and you want to use an Arduino to do it, use Nordic chipsets to do it. So let's build something. In the tradition of hardware demos everywhere, I'm going to make an LED blink on and off. Well, we're going to be slightly more complicated in that. We're going to build a smart light switch, one where you can turn the light, the LED in this case, on and off using a physical switch as well as via Bluetooth. We're going to create a Bluetooth single service with two characteristics. A read-writable switch characteristics. And this characteristics we'll use to flip the switch on and off. So flip the LED on and off. The second characteristic called status, which we can subscribe to, is set as notify, for us to be told if the light is being turned on and off. Because if it can also be turned on and off by the switch, our app, if we have an app that's making use of this smart light switch, might be out of date. So we need to notify the app if someone pushes the light switch to turn it on and off. We also need descriptors. Now, these are optional, but we can use something called characteristic user description, which is a UUID. It's a SIG-approved one of 2901 to provide text description for characteristic values. Now, this is a standard UUID, and tools that know about it can use it to populate the user interface. So if we're building a generic thing that talks to light switches and light bulbs and other various things, we can use this to populate our user interface, which is handy. And as I said, we're going to need those two characteristics because we'll provide the physical switch that the user can push to turn the light bulb on and off. And you don't need the BLE to work this switch because unlike a lot of them, it's actually still a switch. So the other thing to note is that this hardware diagram basically means I've got an LED, but I could quite easily just pull the LED off and put a relay on and attach it to an actual lamp, and the hardware would pretty much be exactly the same, and the software would be identical. So let's switch this down, and let's actually go and build something, if I can. Just maneuver this into place. There we go. OK, so two, hurrah. OK, so the first thing we'll do is let's put the hardware together and then write the software, shall we? So this is the Adafruit BLE Bluefruit board that I was talking about, and this is just an Arduino Uno. Everyone's come across Arduinos before, right? It was in the title of the talk. I don't think anyone would be here if they hadn't come across one. Hands up if you haven't. Yay, OK. So let's just, we'll grab wires and we'll start wiring this up. So this is an SPI connected board. So we're just going to connect it up. Yellow. So I could have used an integrated board here, but it would have been, a bit less fun. 11. So the required line is, 10. So this is then next one is ready. So that goes into 2 there. And then we have reset. So we skip act and we have reset here, which goes into 9. Then we have a ground wire, which we're just going to pull into the rail here, and a 5-volt wire that we're just going to pull into the other rail here. OK. Then we're just going to use, we're just going to power this rail. We're going to put the ground in, and we're going to put 5-volt in here. Make sure I actually get this in the right pin. All right, so that effectively is the BLE board wired up. Right, so LED. Make sure I get this right around. We're going to put a resistor in series so I don't blow the LED up. And that one's going to go into pin 3. And I also need a ground wire for that, of course. If anyone sees me making a mistake, please tell me now. The other thing we're going to put in is a button. I couldn't find something that looked amazingly like a light switch immediately in my hardware drawer, so I've got this momentary contact button. But we're going to make it work like a proper light switch. We're not going to make it so that you push the button and the light comes all on, and then you let go of the button and the light goes back off again, because that would sort of suck. So we're going to hardware debounce this. So this is, you're taking the button, you're pulling it down to the ground state when it's not connected. If you don't do that, the button connections float, and you get ones and zeros coming down on the pin, which means that you get your thing triggered on and off every so often, which is not a great thing to do. So we're going to debounce this. OK, and there to there. And hopefully that's it wired up. OK, so let's write some software. All right, how is that text size for people in the back? Very small. Oh, that is very, very small, isn't it? Wow. OK. Yeah, I can't see that at all. Right, OK, let's go. Arrangement, mirror. How is that for people in the back? Is that better? OK. OK, so as I said, we were wiring this up with SPI. So the first thing we're going to need is hash include spi.h. Again, if you see the spelling errors, because there will be spelling errors, shout them out. I actually want that type of bracket. Then we want BLE Peripheral.h. Anyone? Is that how you spell it? I think so. OK, and then we're going to hash define some pins. LED pin was 3. Our button pin was 4. BLE request was 10. Thank you. I just spotted that. Ready pin was 2. And our reset pin was 9. Now we want a BLE I can't spell peripheral. This is going to be a really bad thing for me, isn't it? OK, BLE Peripheral, BLE Peripheral equals BLE Peripheral, BLE request, BLE request, BLE ready, and BLE reset. So this is just basically telling it where to find the chip. Then we're going to define a BLE service, which is going to be a light switch, which is a BLE service. And I'm going to give it an FF10 UUID. So I'm slightly cheating there, but there we go. I wasn't going to type out 128 characters. I'm not that dedicated. So that's going to need a BLE some characteristic, yay. So switch characteristic. There we go. Equals a BLE characteristic, which I'm going to give an FF11. And it's going to be BLE read or BLE write. This is so much easier than with the new Arduino IDE that actually does syntactical highlighting. Let's just copy and paste that into the next line. We're going to call this a state characteristic. And this is going to be BLE notify. Yes, all right. I'm going to save it on the desktop. Go away. All right. So we also need some descriptors at that point. So BLE descriptor, yay. So switch descriptor equals BLE descriptor This has a UUID of 2009, so that's the character description thing. We're going to call it a switch. And let's copy and paste that again. Whoops. Really? Sorry, what? BLE car characteristic. Yeah, it means it's passing a character. No, thank you. But these, the two descriptors are supposed to have the same UUID because they're the same type of object that we're passing, a character descriptor. OK, so then in setup, we're going to do a serial.begin 9600, pin mode, LED, pin outputs, pin modes, button, pin inputs. We're going to take our BLE Peripheral, and we're going to set local name to light switch. Then we're going to take our BLE Peripheral. We're going to set device name to smart light switch. So the device name is actually on the generic service. So there's a generic service that all BLE devices have. And this is we're setting the device name. The library is actually setting the device name inside this generic service. The local name is the name of the local service, so the local service we are creating here. Depending on the piece of software that's consuming this BLE service, it'll look for one or the other, and you can't really tell which one it's doing, so it's wise to set them both. Anyway, we now need to establish our service. So let's take our BLE Peripheral. I'm going to copy and paste this because I'm never going to spell it right this many times. We're going to add attribute. Let's actually copy and paste all of that because I'll never spell that right all of the time. Light switch. So this is us adding our service, our light switch service. We're going to add the attribute switch characteristic. Yeah. Thank you. We're going to add our switch descriptor. And then we're going to do the exact same thing for our state characteristic. We're also going to add an event handler to our switch characteristic. So let's take the switch characteristic and set event handler, BLE written. So this is a routine that's going to get called when this BLE characteristic is written to. And let's call this switch characteristic written, because, well, why not? Then what we need to do is do a BLE peripheral dot begin. So that just begins the BLE service. And just in case we actually get to the point where I'm going to have to go to the serial console to debug this, let's hope we don't get there. Let's just print something to the serial console. And that's our setup, effectively. We've created a service, we've created attributes, and we've started the service. So inside our loop, we're going to take our BLE peripheral and poll. This is the thing that actually goes and polls this bulletin board that I've talked about. It handles all the BLE services. Effectively, this abstracts away 99% of everything you had to do with BLE. So it's really a rather nice call. It tells the library to handle all of the Bluetooth processing for you. OK, since we're going to need something to handle the button state, let's go add some variables up here. So int current state. an int debounce state, because as well as hardware debouncing it, that's not how you spell debounce, is it? No. OK, so as well as hardware debouncing it, I'm also going to software debounce it, because I don't trust buttons. They're squirrely little things. So we also need a switch state equals 0. So the initial state of the button is the light should be off. OK, so let's take the current state is digital read of the button pin. And then we're going to delay 10 millis. And then we're going to go debounce state equals digital read. How am I doing for time, by the way? I have 4 minutes left, did someone say? Wow, OK. I'll stop annotating as I type then. So we're going to take the current state is not equal to the switch state. And if the current state is equal to the debounce state, so basically if the button is been pushed and it's been pushed to the right, that's all fine. And then inside here, we'll actually put some code. But first of all, let's just write that callback. So switch characteristic. I'm going to copy and paste that. Written is BLE central, BLE characteristic. OK, so if switch characteristic value, so if the value that's being passed is not 0, so I'm worried there because it didn't indent properly. That probably means I'm doing something wrong. So if someone can... Thank you kindly. So yeah, OK. Digital write, LED pin high, and LED state equals 1. We'll also need an LED state as well as a switch state, because they're actually separate things. And else, oh yes, OK. So also state characteristic. Yeah, it shouldn't. You didn't, because the switch characteristic is defined up here. Maybe I spelt it wrong. State characteristic dot set value 1. OK. And in here, we basically do the exact opposite. We take that low, we set this to 0, and we set that value to 0. So basically, if we tell it to go high, it goes high. If we tell it to go low, it goes low. At this point, let's go back to the button bit. Yep, there we go. So if our LED state is 0, we are going to do absolutely nothing in here. Because at that point, this is the button up. The button is coming back up. So we've pushed the button. The button is 1. We're going to do something if it's 0. This is the button changing to state 0. So it's going to be nothing. This is the user's finger coming off the button. So basically, if I push the button will go high to 1. Yeah, and I'm pulling it low. Sorry, yes, I see what you mean now. So let's just take the Switch characteristic will set the value. So basically, only on the button push down, we'll set the value to 1. We'll also set the state characteristic to 1. And of course, we'll actually turn the light on. LED state 1. And so f LED state equals 0. Oh. I've missed some code here. There's definitely some missing code. All right. That's what I'm doing. OK, I'm going to just quickly bounce out because we're running late. So I'm going to bounce out and go to the one I prepared earlier, which is a cheat, but there we go. Because we're almost done. So where did I go wrong? OK, there we go. This is the thing. This is what I should have been doing. So if current state is low, the button has just been released. Else, then we actually check what I was doing there. So what I forgot was what the loop inside is. If the button is low, the current state is low, then the button has just been released. Does that make sense? Yeah, OK. So at that point, the button has just been released. You do nothing. The button is just being pushed down for the first time. Then if the LED state is 0, then at that point, you turn the LED on. And if the LED state was already on, you tell the LED off. And of course, right at the bottom, you set the current switch state to the current state you just changed. So it knows whether it's changed. Yep. And you can see everything there is the same as I had. So let's just, we've got an Uno. It's not connected up yet. There it goes. OK, so let's just upload. Yep. Whoop. And of course, normally I take my phone out of my pocket not to interfere with the radio mic, but of course I just realized I need my phone to do the demo. So yeah. All right, you can tell that if we push the button, the LED goes on and off, which is good. I'm going to use something called the light blue app, which you cannot see. So I'm going to move it into frame. You can see our smart lights. Can you read that at all? Is that readable just? OK, we see our smart light switch service there at the top. You see we get our switch and our state characteristics here. If I just go to state, I can listen for notifications. And I go back here. And if I push the button, you can see I get a notification at the top there. This is actually changing from 0 to 1 there. You might not be able to see it. I'll just push it again. See the state comes in. I'll wait for it to disappear this time. And you get another notification when it goes. And you can actually go to the switch. You can write a new value. And we're just going to write a 1 and turn the LED on. And then write a new value and turn the LED off. And you can see the notifications also turn there. So you get the notifications both from the button push and from the Bluetooth itself. So that's it, really. That was a very quick look at how to build a BLE device. Thank you.